Okay, our next speaker is Sai from IIT Bombay, and he's going to talk about measurement-induced continuous time crystals.
Thank you very much. So let me begin by thanking all of the organizers. It's an absolute pleasure and my privilege to be here. So today I'm going to talk to you about work that basically started off with work in synchronization physics, synchronization of nonlinear oscillators in the context of quantum mechanics. So there's a bunch of papers here which are not directly relevant, so I've separated them a little bit. There are two which are relevant directly, and so the one that I'm going to talk about is the very top one, and of course two of my co-authors, Mithun and Parvinder, are actually in the audience, and Mikhail is at KO, and he's the other author. Okay, so with that, let me get on with it. So let me just, I'm sure all of you are experts here, so but let me just introduce, just for the sake of consistent notation, this workhorse that I'm going to basically take for a ride. So if you have a density matrix, you can of course vectorize it. There's just an isomorphism, if you want to think of it that way, an isomorphism between outer products and tensor products, and you can vectorize it into this shape. And then you can write a vectorized equation. And so what I will refer to as the Liouville superoperator is this object, which is basically just the thing that generates the evolution of this density matrix. And so with this, of course, you can immediately conclude basically the long-term dynamics, especially if it's a time-independent Liouvillean. You can conclude the dynamics of it, and especially the long-term dynamics, which is what we'll be interested in. And so the long-term dynamics actually is dictated by the eigenspectrum of the Liouvillean superoperator. So what I've done here is drawn a diagram which has classical mechanical orbits sitting here to kind of draw your to share our intuition with. And so if you have this kind of Liouvillean eigenspectrum, it can only have negative real part of the eigenvalues. And so you could, of course, have things that are just purely decaying. You can have complex eigenvalues, which have both real and imaginary part, which means this is the analog of classical mechanical spirals. And you can just have a steady state here. And this one is the one of interest, which is basically oscillating coherences. So these are analogs of centers, which is just harmonic oscillators in classical mechanics. The big difference here is that these centers are basically going to be stabilized by many body physics. Okay, so again, to kind of pay homage to periodic driving, quasi-periodic driving, you could of course do this whole thing with some sort of periodic drive. So if you have a master equation where, just for convenience sake, I've written this Lindblad form. I have an H and then some dissipators which depend on some operators X of T. Then you could, if there is this kind of neat periodicity of both the Hamiltonian and the Lindblad operators, which basically means that there is some microscopic model that you're driving periodically, and then you derive the equation. Then you can construct basically the Floquet propagator. Well, you can construct the Liouville propagator, and then you could look at basically the Floquet propagator. So you could look at the one period Floquet propagator, and this eigenspectrum, the fact that it produces DTCs, was discussed earlier in this session. Okay, so but this is not considered here. I'm not going to talk any more about this, but except for one place where basically there is a formal connection. Okay, so in this context, let me introduce time crystals. I feel very much out of my depth here because two of the co-authors of this paper are sitting here, but I power on nonetheless. So the idea here is to consider this driven decay model. So this is being driven by basically a strength omega and a dissipative rate kappa over S, and the dissipator is S minus. So what you see is that for any finite size of the spin, large spin S, you see basically oscillations, but the oscillations die out, basically. And whereas in the thermodynamic limit, basically, you see the oscillations persist, but only if omega over kappa, which is the drive strength by the dissipation ratio, which is normalized in this way, is actually larger than 1, right? So this was pointed out in this paper. And so you can imagine it basically as a bunch of spins that are executing oscillations periodically in time. And so this goes back to this whole conversation about breaking the symmetries of the underlying Liouvillean. In the DTC case, it's a discrete symmetry, and in this case, it's a continuous symmetry that is broken. Okay, so so you can identify, one can identify basically two phases, one of which is a melted phase for omega over kappa less than 1, and melted simply refers to the fact that even in the thermodynamic limit, you don't see this persistence of oscillations, whereas you just see the oscillation, the steady state is basically time independent. And across this omega over kappa equals 1, you see a time crystal phase, right? So this is the transition. Sorry, is there an echo on my mic? Do you want me to pull it on? It's all good, okay. I can hear something funny, but. Okay, so just to kind of warm myself up, let me just do mean field analysis. So you can write what the mean field equations look like. And so the way that you would at the mean field try and conclude that there is a time crystal here is by computing, let's say, the Jacobian to check the stability and to compute the fixed points. And what you notice is that the fixed points have to be carefully analyzed, because this number, which is kappa over omega, I don't know if you can read it in the back, kappa over omega, it's a 1 minus something. And so if that something becomes larger than 1, then this number becomes imaginary, but I'm actually just pointing at the mean field magnetization along the 3 directions, which means that's not a valid solution anymore. So what happens is that these 2 solutions, the fixed points, essentially go from this not being allowed to this not being allowed, this not being allowed, and this basically is the thing that that signals the transition. So at the at omega over kappa equals 1, you can already see that there is something happening here, right? Okay. So within the Liouville framework, how would you work this out? Again, this is just exactly what I just introduced 2 slides ago. So you vectorize the dynamics, and then the steady state is basically this exponential of the Liouville times time acting on the initial state in the t going to infinity limit, right? So it's the asymptotic limit of just the dynamics on the initial state. And so what you do is you consider those eigenvalues, because this Liouville superoperator is not Hermitian, its left and right eigenvectors can be different. So you consider those eigenvalues where the real part is 0, and that's what's written here, mu such that alpha mu equals 0. And you compose basically all of the overlaps with the initial state and the right eigenvalues. And that's basically this oscillating piece here. And then you recover basically the physics that I just told you a second ago. And if you want to identify what's happening here on the Liouville eigenspectrum, what's actually happening is that you start with something that's spiraling, which means it's oscillating, but then it's decaying over time. And then, but the real part of this, which, let's say is over here, essentially just goes and hits the axis. And what that means is it just loses its dissipative nature in the thermodynamic limit. Okay, and then you recover this kind of a diagram, if you look at the magnetization. Now, you can do the same with the, you can actually stare a little bit closer at the Liouville eigenspectrum, and what you notice is that, again, for omega over kappa less than 1, you see essentially that there's this decaying terms here. There has to always be a steady state for CP evolution, as we know. But what happens is that there is basically just a bunch of these decays and spirals which are sitting out. Whereas even for finite size, you can basically check that for omega over kappa greater than 1, there are these oscillating coherences which are developing. They haven't yet hit the imaginary axis because this is finite size. And so how do you go about checking that the thermodynamic limit is correct? You actually just do, just do asymptotics. And so you check with the asymptotics that the real part is going to 0 as you would imagine it to, and then the imaginary part actually is developing some non-zero value, and then it persists in the thermodynamic limit, right? Okay, so this is the story. So I just want to highlight one thing, because this is perhaps one of the big differences in this present work and the one that I'm going to show you in a second, which is how to set up the drive. So there are several ways that are discussed, and one that's perhaps more or less intuitive is that you start with a Hamiltonian, which basically has this kind of quantum optics SX drive S plus e to the I omega t plus S minus, and you just move into the rotating frame. And when you move into the rotating frame, you just it becomes an SX, and that's the collective SX that you see in the master equation a second ago. So you just appeal to optical frequency drive plus RWA, and there is a discussion on what happens if there are counter-rotating terms. Then there is actually flow K-physics here as well, which I'll just leave out for the rest of this discussion. Now, so if you do this analysis at the microscopic level, you can basically just rederive this equation. That's more or less straightforward. But the crucial thing that I want to take away from this slide is that now you have to also tune omega over kappa to actually cross this transition, to make this transition. And you can do it either by basically increasing omega or decreasing kappa, because as you, if you just think of kappa over as some kappa tilde, basically then this ratio of these two things has to go with the size of the spins. Yeah. So these are, B are some Bath operators. So this is basically just asking how you will go from here to here, because when you move into the rotating frame, you also have to have the, when you perform the rotation, it has to be time independent invariance, right? Yeah. So, okay. So I just want to point out that there are some experiments as well if you want to, if you're interested in this. So there is some persistence of oscillations that you can see in basically the intercavity photon number of this experiment, which is basically like a cigar-shaped PEC rubidium atoms. But it's imperfect, and essentially because the drive is not constantly on, there is a turn on, and then there's stuff here, there's experimental imperfections, which I'm not very good at. And there is also a more recent experiment that actually Sarah pointed me to, which I just wanted to include to acknowledge the fact that there's another experiment in this. Again, basically more or less the same setup. Okay, so just with this, before I get on with my part of the talk, I just wanted to point out that this is actually quite a rich field. And so there's a lot more that's been done here. And so I just wanted to give you a flavor of the other kinds of stuff that's happened here in case you're interested in this. So people have studied, so this is Nathan Sharma and Picorio, I think is the first author here, who studied CTCs in essentially generalized models like PQ models. There's work in D-level systems, basically. So this is again, Fernando Iamini's group. There's studies on what happens to what the correlations are in time crystals as you cross the phase transition. So this is these genuine multipartite correlations, which means you remove all K-1 body correlations and you look at what the, that's the word genuine here. And of course, Berislav is coming next week, and he's written extensively on this, including connecting them to spectrum generating algebras and strong symmetries, and I'm sure he's going to talk about this stuff. Okay, so so with that, let me just briefly point out some of my interest in this. So one of my interests is basically to try and see whether I can use this to do something interesting. And so kind of as the first step towards this, we wanted to check whether we could take networks of time crystals and do something like try and synchronize them and so on and so forth. So this is work with Parvinder and Saro, both of whom who are here, and Mikhail. And this is a poster that is available outside. So I just want to briefly advertise that. Now, there's also another recent application, basically on using these time crystals as sensors. So given the fact that there is a phase transition here, there is a divergence, and you can exploit that divergence to basically increase the signal strength that you're measuring. Okay. So with that, I just want to point the problem out, which is we wanted to ask, is there another method to manipulate basically this transition, to cross the phase transition? And the method that we wanted to basically choose was to induce, to get measurements into the conversation, because strong measurements especially are much more readily implementable, they're more easily controllable. And so, you know, we thought maybe that's something that we can contribute towards the story. So this is the cartoon of a central spin model with some measurements acting on it, which I will basically discuss. But there is a kind of perhaps slightly more amusing way to put this, which which is that there are actually two infinities here. One is to take the thermodynamic limit, and the other is basically to take the Zeno limit. And well, essentially, you can just point them at each other and see what comes out. And this is, this is what we were trying to do. So it's It's just that. Okay, so with that, let me again, at the risk of basically boring the experts in the audience, just walk us through measurements and why they have this dominant effect, which I think will play a strong role in a couple of slides. So I just want to think of a generic CPTP map. And so of course I can write rho of T as basically some set of operator sum representation, A rho A dagger. And this example actually is derived from a wonderful review by Kurt and Dan Steck, which I highly recommend. So if I wanted to now, in this dynamics, I'm going from rho 0 to rho delta T, introduce Hamiltonian physics, I would just put in 1 minus IH delta T, and that gets the job done. But that's not measurements, right? That's not the stuff that we're after. So I can think of sticking in one more operator, which is just a B dt, right? And if I now try and do the maths, this, especially this red part that's sitting here, it doesn't preserve trace, because if rho is trace preserving, then if the evolution of rho is trace preserving, then d rho by dt should be traceless. And so I need to fix this at just a kind of linear algebra level. And so what I do is I introduce the square root of dt. So I introduce a Wiener increment, and I introduce a square root of dt, and then that square root of dt you can work out produces a dw squared, whose stochastic average is dt. And this is this C rho C dagger term that we're actually quite familiar in the Lindblad language. And then if you just identify B with minus C dagger C over 2, then this is trace preserving for arbitrary operator B's, operator choice C. And so this is one way of looking at this. But more importantly, there are two pieces of kind of contact here that I can make, which is one is that if you keep this DW term, basically, which is to say, if you want to keep the measurement record, then you go back to these measurement-induced phase transitions that Saro told us about a couple of days ago. I'm not going to do that. This is just a dissipative phase transition, but here it is just one step away for us. But what I want to point out is basically the Zeno limit in this context, right? So in this context, the Zeno limit is simply the following statement, which is that for every increment dt, which is where I wrote all this stuff, I'm sorry. For every increment dt that I write something deterministic, which is like a B, I actually need to put in basically something that's a dw squared. So if I think of Hamiltonian evolution, which is the thing that I'm trying to compete with measurements, for every time increment dt that the Hamiltonian evolution acts at, that's the cartoon of the black arrows on top. The small black arrows in the bottom basically are just pointing at the fact that the measurement acts much, much faster, right, as order square root dt. And so in each interval here, you have a huge number, and then as dt goes to 0, the measurements dominate, right? So this is the reason why typically, if you just look at just any standard textbook on open quantum systems, measurements will dominate. The steady states are always dominated by the measurements, and there is almost nothing to discuss. It's just the Hamiltonians will change the basis, but I'm oversimplifying that. So in the context of Zeno, you can actually think of this in another way, which I also find intuitively correct, whereas the derivation on this, so this derivation I'm showing you is from this paper by Dan Lidar, Facci, and Saverio Piscazio. I also refer you to this Burgath paper, which has some commentary on it in the recent past. So if you want to think of a unitary evolution interspersed with some kicks, and then just take the limit of the kicks going to more and more frequent kicks, so the limit of n going to infinity, then you can actually write down basically, so to simplify, you can basically take out these kicks because that's the dominant physics that's happening. So you can write this V operator, which is U dagger to the n acting on UN, which means you're just taking out this U1 to the nth power, which is the kind of most dominant physics here. And in this limit of n going to infinity, you can write what this evolution operator U is, and you can try and work out what the physics of it is. And sorry, it seems to have exchanged the two. The physics of it basically works out to be something that, so U in the n going to infinity limit essentially looks like this. So it's a projector onto the measurement basis that you've done, and along with basically, along with projecting the Hamiltonian, there is just some dominant piece which comes from the fact that you have a measurement there. So the bottom line is the way in which the Hamiltonian gets modified is actually to get projected into this thing. And this thing is generically called the Zeno subspace, right? And so you can have dynamics in the Zeno subspace, but the Zeno subspace basically, for our discussion is basically just this thing where H commutes with P. Sorry, PZ is the same as, one of these P mu's basically. And so in this context, basically, let me pose the question. I have about 20 minutes to go. So the question that I want to ask essentially came from me just reading one of these reviews. This is Davide Rossini, and essentially what they say is a projective quantum measurement. Measurements of observables disentangle degrees of freedom and tend to decrease quantum correlation, similar to decoherence, right? And again, I think this is, I think all of us know that this is a point, but it's not all of the point. And and that's why I put a star there, because there's a ton of reservoir engineering that all of us are involved in, which involves generating entanglement and using the bath to do it. So I put a star there because I think there's some implication about local measurements here, and very strongly so. But nonetheless, this is another way to motivate the work. And so the question is, if I wanted to implement this kind of a time crystal, then what could I do? Well, what has been done in the experiments that I've just shown you is that you raise omega, basically. So you take omega and you scale it up, and hopefully it doesn't heat the system, like is the case with a lot of chemistry experiments and quantum experiments, where the environment picks up a lot of the field that you're putting into the system and then just heats up. Hopefully this is all not an issue, and this is controlled, and this model remains valid. And I think the experiment is proof that this is the case. But we just wanted to ask, can we go there? Can we actually just increase the measurement strength and instead just leave all the power, the coherent power that is put into the Hamiltonian kind of more or less order one? And so that's the logic of this simple calculation. And so the calculation is quite straightforward, which is, let's say that I have a system and I have an ancilla, and they're interacting with each other with some Hamiltonian evolution. Now, what I do is I just measure the ancilla very strongly. And if I don't monitor the outcome, then it's just basically modeled well in some limit by Lindblad evolution. And now the question that I'm asking is, in this limit, what happens to the system evolution, right? And this is actually well known. And so what happens to the system evolution is given by basically this logic, which I'll explain to you. So if you take d rho by dt, d rho AB by dt, and AB are the two systems, and I write the evolution in terms of two pieces. One is basically a Liouvillean, which basically just carries the Hamiltonian. So it's the Hamiltonian of each subsystem and the interactions between them. And the second is basically a dissipator whose strength I'm going to turn up at some point. Then this is the total Liouvillean. Now what happens, just logically? What happens is that if I just turn up the dissipation quite strongly, then basically the B subsystem is stuck in the states that are defined by the zero subspace of that measurement, right? And so this dissipator basically projects the B subsystem onto some state, which is what's called rho zero here. And what happens is that the effective evolution that A sees is essentially just projected onto the consequence of that subspace, right? You have to take that physics forward and work out what happens. And so that's what's written here. So the Liouville superoperator again has its eigenvalues and eigenvectors. And these eigenvalues and eigenvectors, basically the zeroth eigenvalue is this, basically the kernel of the dissipator. And you just get pushed into the kernel of the dissipator, and then the effective physics of what's happening on the A subspace is what you have to work out. Okay, so there are formal ways to do it, but essentially what happens is you have to do a perturbation theory on the dissipation rate. And if you do that, then you essentially end up with an equation like this, which I will just explain. Actually, this is something that is quite familiar to all of us who've done approximate inverses of matrices or operators, right? So this is a equation that shows up all over the place in perturbation theory and so on and so forth. And so what this is basically that effectively to first order, you're just getting projected onto the onto the K space. But then there is a correction here, and this correction is something that I'll explain just now, which is so you can, again, it's a standard kind of perturbation theory correction, which is you go from the P subspace through K. K is the, so let me just back up just for a minute. K is the Hamiltonian part and D is the dissipated part, right? So what you do is you go from the P via the K to the Q subspace, which is 1 minus P, and then you go back to P, right, with the 1 over gamma, right? And so this is understood basically as the dissipation on B, the strong dissipation on B, inducing an effective physics on A. And then there is some correction terms which we have to keep track of, which we did keep track of in the paper to make sure that the approximation that I'm presenting to you is correct. Okay. So what we did was we applied this whole thing to a central spin model. So the central spin is as Z, and then there is a peripheral set of spins which are basically I's. And now we want to see what happens to the physics here, right? And this J is a bit unusual, which I'll show you in a second now. So so what we did was so again, this is the central spin model. And then what we first did was basically took the full central spin and wrote out the master equation, right? So this is with the strong dissipator gamma that is acting only on the central spin. So this is an S minus, which is acting on this central spin. And then if you derive the effective master equation for the peripheral spins, what you get is a minus IH rho, and then a 1 over gamma times a dissipator on rho plus some correction terms which you have to keep track of. And here is two things that I have to mention to you. Is this H has some terms that have to do Z alpha have to do with this J matrix, and also the Lindblad operators have some contribution from the J matrix, right? So what I'm going to point out to you is basically a particular choice, which is if you make the choice JXX equals JYY and JZZ is some other number, 2 omega A, and then JZX is minus 2 omega. So you can recognize that there are these capital omegas and small omegas floating around. And this is essentially exactly to make contact with the BTC, right? With the standard continuous time crystal, Yamini et al., Jonathan and Saro here. And so what does the dynamics look like of this model? So what we did was we just considered the mean field equation. So everything is mean field decoupled here. And then we adiabatically eliminated basically the central spin because it's very strongly measured. So it's fast dynamics, it just gets out. And if you adiabatically eliminate the central spin, then what happens is that you can take this solution, stick it back here, and you see persistent oscillations of the peripheral spins. Just another way of checking that we're on the right page. But actually, if you look at the equations very carefully, what happens is that the central spin is actually pegged to the mean field of the peripheral spins. And because the peripheral spins are oscillating, it's perhaps not very visible from the back, I'm not sure. But these oscillations are order 1, and the central spin is oscillating at 10 to the minus 2. So there's very, very small oscillations along the YZ direction. It's strongly pinned to the X direction. And so to the Z direction, sorry. And so along the XY direction, there's small oscillations here. So, okay. So again, we have to make sure that we check that this is, the mean field is actually telling us perhaps the truth by doing Liouville theory. And so one way to kind of make sure that everything works out, because there are 2 independent objects till now, because the Zeno limit is just the strength of the measurement, and I take it to infinity and I can do it however I want. But then there is a different object, which is the thermodynamic limit, and I'm trying to take that to infinity as well. So I just peg one to the other. So what I do is I define basically the dissipative rate gamma, which you've seen till now. It's going to go to infinity, but I call it small gamma times I. So when I take I to infinity, I don't have to do anything else. For finite small gamma, this is just in the Zeno limit already. But you'll see that already even that makes a huge difference. So with that identification basically of gamma equals small gamma times I, you recover basically the standard CTC that I just showed you on the first couple of slides, with the identification of the dissipative rate as being JXX square over gamma. Okay, so this more or less completes the analytical proof that this should work. And now what we did was we just looked at the Liouville eigenspectrum to make sure of the full central spin model. So this is the Liouville for the full central spin model, just to make sure, just to check what's happening. And let me explain to you in words what's happening here. So I want you to notice 3 or 4 things. So there are these Romulan warbirds here, which you should just ignore just for the moment. I'll draw your attention to them in a second. Notice that there are these thin cigars. There is this red cigar, this blue cigar, and then this black cigar here. And the reason that they're so skinny is basically because they're pegged to basically, real lambda is pegged to gamma. And gamma is going to the thermodynamic limit. So what I want to say to you is that as you increase to the thermodynamic limit, there are 3 bands in the Liouville eigenspectrum that develop. These 2 are transient bands. And the transient bands run away to minus infinity, which means these things die extremely quickly, right? So in finite time, these 2 things are completely irrelevant, basically. And so you can just ignore these 2. And this is the one that's actually approaching 0, and this is going to become the time crystal. And so you can see that basically there is also oscillating coherences in this. So there's this imaginary part which is switching on, even though the real part is going off to 0. Okay, but this is the full theory. And what we did was we also compared it to the effective theory that I just showed you, right? So you can actually calculate either from the full CSM or from basically the Yamini effective equation that we think is the correct one. And basically they agree with each other. You can just see at the Liouville eigenspectrum level, they agree with each other. And the numerical inaccuracy here is under the numerical inaccuracy that you would allow given the fact that you've specified these numbers to some precision. Okay. Okay, so with this, I have about 8 minutes. So let me begin concluding by pointing out what I've just described to you as a picture. So this is a phase diagram of what I've just shown you. So this is the small gamma, which means that there is actually the actual dissipation rate is this multiplied by the total number of spins. And on this axis is the total number of spins itself. And what I just showed you was that below a certain threshold of small gamma, which has to do with the term that I ignored in the master equation, it has to do with some ratio of the Hamiltonian infinity norm of the Hamiltonian to the dissipation rate. We actually have to consider the full spin star model. Otherwise, you get deviations from the approximate theory. And this is no good, basically. And after you cross this, it's a soft spot. After you cross this, what happens is basically, you can ask what happens for finite number of spins. For finite number of spins, we have 2 infinities again here. One infinity is the strong measurement that I've just turned on, and the other infinity is the thermodynamic limit. If I don't turn on the thermodynamic limit, which is to say I'm at finite number of spins, and I only turn on the Zeno measurement, the Zeno wins always. So what you get here, and this is what's described here, is that you get a bunch of eigenvalues of the Liouville superoperator, where the real part of the eigenvalue is actually non-zero and it is negative, which means it's dissipating. And so you basically just get the simple fact that if you turn on a measurement and ignore the measurement results, the thing dissipates away, right? That's it. There's nothing more reasonable. And this is just some steady state statement here. On the other hand, if you measure strongly enough, right? This is the watch pot never boils limit. Then you get into what's called the unitary Zeno regime, where you basically get into that analysis that I showed you, which is you can get projected into a subspace and perhaps you have some unitary dynamics in that subspace. But again, this is just a finite size object. There's no phase transitions here. But what happens is that if you now go into the thermodynamic limit, which is what I've indicated there, what you have is actually just exactly the Yamini et al. Time crystal. And because of that, you actually go from a melted time crystal to a oscillating time crystal. And so we label this the Zeno time crystal, just to be cool. So the full phase diagram is this, right? And so the whole point is basically that there are 2 infinities here. One is the strength of measurement that you can turn on, experimentally, perhaps a convenient tool for us to kind of take forward in the discussions about both discrete and continuous time crystals. And the other is basically the thermodynamic limit. And you can get them to compete with each other in interesting ways to actually reproduce oscillations which persist in the thermodynamic limit. But this time they persist in the thermodynamic limit only if you actually also turn on very strong measurements. So if you have weak measurements and you're in the thermodynamic limit, you only get a melted time crystal. It doesn't oscillate, right? Okay. So with this, let me conclude. I have 5 minutes left, so I'm happy to take questions. So as I've emphasized to you, this is just a perspective, which is that, Zeno, like thermodynamic limit, is an infinity. So we've tried to get them to play with each other. And the central, perhaps straightforward technical point from perturbation theory that I can share with you is that strong decoherence on an ancilla would induce that 1 over n or 1 over s effect that I think is very interesting to carry forward when we discuss this relationship. Actually, the reason that this 1 over s is important is because, well, at least my understanding of it is that the Hamiltonian appears as basically Sx times rho. So it just appears, if you take scaling of it, it just appears once. S appears once. Whereas the Lindbladian appears as S minus rho S plus, which means it's quadratic. And that's why you need a 1 over S there for it to compete with the Hamiltonian term, right? For it to not overpower the Hamiltonian term. And now we have a method to basically concretely produce that. And more or less, this is just a simple example to show that this can be done all over the place. Okay, so yeah, this is exactly the point I just made. And perhaps this contributes towards our future studies of both dynamical and measurement-induced phase transitions. Okay, so with that, let me just conclude by acknowledging folks who are first of all not here, but Yashma is online. So I'm continuing studies of time crystals with Ankan, who's a wonderful undergraduate who's moving to Caltech, and Yashma, who's a PhD student in our group. And Midun and Parvinder are of course here, and Mikhail is a friend and collaborator, and Saro is of course in the audience. So with that, I thank you very much. So here are some references. This is the one that I just presented, and this is the one that's in the poster outside, and there are several more. And thank you. I'm happy to take questions.
Any questions?
So I think I probably got a little bit confused about this last example about this Zeno time crystal. So you have a central spin model.
Yeah.
So all the peripheral spins, they don't talk to each other, right?
No.
And so then you basically measure the central spin so strongly that it's always down, except for 1 over gamma fluctuations.
Yes.
But that basically means that all the spins just feel an effective magnetic field. They don't interact with nothing.
Yeah, so the point is basically there are 3 terms here, right? So this is the central spin, right? This is a peripheral spin, which is just defined by this IZ.
Right.
And then there is this J, and J is doing all the heavy lifting here, because you can see that there are tons of terms here which are non-zero.
Right. But I guess my point is that now the model, if I neglect the 1 over gamma term, the model is just non-interacting spins in a field which is generated by the external field they had plus the coupling to the central spin.
Yeah, so I have ignored the fact. So when you say external,
well, the central spin. So there's a central spin.
Yes.
This is frozen. This gives a mean field.
Yes.
Effective field on the peripheral spins.
Yes.
And that's it. But then if I put infinitesimal disorder on any of those numbers, this will just decay to 0 immediately.
I don't see the intuition that you're seeing, Dries, but
I mean, because it's just spins with a random field.
No, yeah, this is not the case. So the point is basically that if you look at basically these quantities, these are fixed for all of the spins.
Yeah, but
that's, yeah.
I mean, I'm saying that your time crystal just oscillates at some frequency which is given by these omegas, but
yes.
I mean, then it's not a time crystal because it's not stable against any infinitesimal perturbation. If I add epsilon noise to this, you'll just get some Gaussian decay of the signal.
I don't see that intuition immediately, but let me just say one thing, which is, I don't know where this is. Yeah, so this is actually doing all the heavy lifting, which is, so if you look at this, this is just not the Hamiltonian. So, the J being projected is not the only physics that's happening here, actually. This term actually contributes some Hamiltonian physics.
Right.
And this is important.
This I get, but still, I think you're just describing a bunch of non-interacting spins that oscillate at some frequency, which means that if you would add some noise to your couplings, it wouldn't oscillate anymore. Or in other words, if you change your omega by and make omega instead of 1, you make it 1.5.
Yeah.
Your crystal will now oscillate at 1.5, right?
If you have inhomogeneity in J.
In J, exactly.
Okay, I don't know.
Exactly. I mean, that's the whole point of a time crystal, that it should not depend on the disorder in the sample. Otherwise, everything is a time crystal that doesn't interact.
No, yeah, I think this is stabilized by exactly the same physics that that the standard. Do I need to do anything with this? Okay. This is stabilized by the exact same physics that the standard CTC is stabilized by, right? So in the sense that that's a zero-dimensional model, blah, 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 you're having the same, you know, we're making the same discussion.
No,
If you
because
go there and you break the permutation invariance, right? What happens is a question that you can ask.
okay, yeah, we should talk about it, but I think it's very different.
Okay. You mean gamma 0, Saro, or this? Yeah, there is no phase transition here. No, it's a soft, it's actually a crossover, and it's a very soft limit, basically. Just has to do with the fact that you want to make the approximation work. Yeah. In fact, in principle, you could actually see some interesting physics here. It's just that you have to look at the full central spin to see what's happening, right? I mean, I don't expect anything interesting to happen here because there's a melted crystal down south, to the west of it.
Yeah, so yeah, I have the same question about this one. So these lines are like, they are strict lines or phase diagrams?
No, yeah, so this is explained in the caption of the paper, sorry. So these dotted lines are basically soft lines. They really don't, you should not read them as phase transition points or anything strict, because they just have to do with controlled approximations, basically. So here is one controlled approximation that allows you to go from central spin to the effective time crystal model. And here is another which allows you to go from finite spin size to infinite spins. So, you know, thermodynamically large number of spins. So that's why there are these little hints on there.
Yeah, but that thick line is strict, is it?
That's a strict one.
Okay.
Yeah.
And the other question I have is like, so you have a spin that is coupled like with exactly same coupling to a bunch of spins, right? So if you do not have this measurement, so does that model have a well-defined thermodynamic limit?
This is, yeah, it's a complicated question because you're just saying, does the central spin model have a thermodynamic limit?
Yeah.
Yeah, I appeal to the wisdom of Bethe Ansatz, blah, blah, blah.
Okay.
I've tried looking. There seems to be some, you know, I'm confused about it. Let me say it this way. Yeah.
There are no questions. Let's thank Sai again, and it's time for lunch.